Okay, so you had 4 suggested questions to try. They were on page 137. That's a 7. It just doesn't look like it. Question number 1 says, find the weight of a 2.3 kilogram bowling ball on Earth. Weight, Fg, is equal to mg. And so a 2.3 kilogram bowling ball, and it just says on Earth, so 9.81 meters per second squared. Type this in your calculator, and you should get 22.563 newtons. Number 1 is done. Number 2 says you have a weight of 652.58 newtons down while standing on a spring scale on Earth. So they're telling you this time the Fg. It's 652.58 newtons. And this one's down as well. Gravity always pulls us down. Okay? And so the first part of number 2 wants your mass. So we know Fg equals mg. So m will just equal Fg divided by g. So that's 652.58 newtons that they gave you in the question, divided by 9.81 meters per second squared. And when you do this, you should get an m of 66.72256 kilograms. All right, part A. Part B says, determine your weight on Earth near the North Pole. So now you have to go to page 132, and you have to find the little g at the North Pole. And the little g at the North Pole is 9.8322 meters per second squared. And also down. It's bigger at the North Pole because the Earth is not a perfect sphere, right? The Earth is like a circle that someone put a hand on the top and a hand on the bottom and squished together. So the Earth is actually flattened at the poles and bulging at the equator. So because it's flattened at the poles are actually closer to the center of the Earth than the equator, points at the equator are. So that's why the little g at the North Pole is bigger and the little g at the equator is smaller. So for part B, Fg is equal to mg. So it's this 66.72256 kilograms that you just found in part A, and you're going to multiply that by 9.8322 meters per second squared. And when you do, you get an Fg of 656.029556 newtons. So you weigh more, which should make sense because you're closer to the center of the Earth, so the force is going to be bigger. And then part C wants you to find your weight on the International Space Station. So your weight on the International Space Station, so Fg equals mg. Again, it's 66.72256 kilograms. And at the International Space Station, little g is 9.0795 meters per second squared. Lots of people think that because the astronauts are floating in the International Space Station that there's no gravity. But if there is no gravity, that International Space Station would be hitting out to the next nearest star. So there's definitely gravity, and there's actually quite a bit. Like, it's still over 9. We'll get back to why they're floating in a second, but first let's do the answer. So the answer is 605.8075 newtons. Now, the rest of the question in part C says, why would this value be impossible to verify experimentally? And the reason is because the astronauts are floating in the International Space Station. But why are they floating when there's actually a force of gravity on them? Well, the reason they're floating is because here's the Earth and here's the International Space Station, obviously not drawn to scale. And the International Space Station is actually falling towards the Earth. Gravity is actually pulling it down. It's just that it was given an initial velocity this way, And so as it tries to go this way, gravity pulls it in. And so then it tries to go this way, but gravity pulls it in. So it's actually falling around the Earth. And the astronauts inside are falling exactly the same speed, with exactly the same force. The acceleration due to gravity is exactly the same on them, and so it looks like they're floating. The best way to understand it is if you've ever been at an amusement park that has that ride where they put you in like a little elevator and they take you to the top. It's called the Tower of Terror. And then when they get you at the top in the elevator, then they drop you in the elevator. So you're not outside exposed to the elements. There's no air resistance, but you free fall. You fall at 9.81 meters per second squared. So if you ever go on this ride, when you do, just as they're about to drop you, let go of a dime in front of you. And as you fall, that dime will float in front of you the whole way down. Now, it's not really floating. Someone on the outside, on the ground, can see both of you falling. But with respect to you, it looks like the dime is floating. And that's what's happening with the astronauts in the International Space Station. They are actually falling towards the Earth, just like the space station is, except they're falling around the Earth because of their velocity. But because they're doing it exactly the same way as the space station, they're floating with respect to the space station. Okay, more on that when you take Physics 12 and we do the planets unit, and we'll talk about satellites. But for now, number 3, a lunar roving vehicle, pictured here, has a mass of 209 kilograms, regardless of where it is. But its weight is much less on the surface of the moon than on the Earth. Calculate its weight in both spots. So Fg of the Earth is going to be equal to m times g of the Earth. So Fg on the Earth is 209 kilograms times 9.81 meters per second squared. So on the Earth, this vehicle has a weight of 2,050.29 newtons. Okay? Now, to do it on the moon, you have to go to page 133 and find the little g of the moon, and it's 1.64 meters per second squared. So then Fg on the moon, which is equal to mg, it's going to be equal to 209 kilograms times 1.64 meters per second squared. So Fg on the moon is going to be significantly less. It's 342.76 newtons. It weighs a lot less on the moon because the moon is a lot tinier than the Earth, and so it has to have less pull. All right, I think I can get number 4 in here. And I know I have a bad habit of writing at an angle. So a 1 kilogram mass is used to determine the acceleration due to gravity of a distant city-sized asteroid. Calculate the acceleration due to gravity if the mass has a weight. So Fg is equal to 3.25 times 10 to the negative 2 newtons, and of course that's down. And so it wants you to find the acceleration due to gravity, in other words, little g. So little g is going to be equal to Fg divided by m. So this 3.25 times 10 to the negative 2 newtons divided by, higher order math, 1 kilogram. Little g is equal to 3.25 times 10 to the negative 2 meters per second squared, which reminds me I forgot to say something on the last video. When we did, what did I do with that sheet? When we did this and we found little, when you do the units on this, you will find the units here are meters per second squared. So mg is kilograms times meters per second squared. And this is what we have renamed a Newton after Sir Isaac Newton. So a Newton is equal to a kilogram meter per second squared. Okay, and I'll say a little bit more about that on the next video. But for now, just know that. So a Newton is equal to a kilogram meter per second squared. Okay?